A dazzling light that is not a quasar or a far-off galaxy may be seen in the lower left corner of this photograph. Instead, it is a supernova that is bursting and has eclipsed almost every star in its host galaxy. Additionally, it is a Category 1A supernova, one of the most powerful explosions in the universe. A supernova is regarded as the tragic ending of a star. It can produce up to 5 billion times as much light as the sun. In fact, the supernova explosion of the supergiant star Betelgeuse will be so bright that it will be visible throughout the day for up to 3 weeks. Astronomers are eager to witness these dying stars because they offer valuable insights regarding stellar evolution and help cosmologists determine the pace of expansion of the universe by precisely determining the value of the Hubble constant, the most contentious quantity in cosmology. However, recently, astronomers have discovered an oddity in a distant explosion. The star has somehow withstood its explosion and now is glowing brightly than it did before. The star appeared to have confused astronomers by pretending to die. However, how did the star endure the devastating explosion that should have destroyed it? And what does these findings add to the mystery behind star explosions? Hello there, and welcome back to the Discover Space channel, where we explore the universe and the mysteries that lie within. Be sure to subscribe if you haven't already, and let's get on to the video. This explosion was initially seen by Hubble in 2012. It is known as SN2012Z and is located in the spiral galaxy NGC 1309, 120 million light-years from Earth. When a star with a mass ranging from 0.07 solar masses to 10 sun masses achieves its final stage of development, a white dwarf forms. These stars are unable to support full-scale carbon fusion. In essence, the parent star's exposed carbon-oxygen core is what makes it so dense. The maximum mass of a white dwarf star is 1.4 solar masses. The white dwarf will further collapse to produce a neutron star if its mass exceeds this threshold. The Chandrasekhar limit is the term given to this mass limit, which was developed by an Indian astronomer by fusing the principles of statistical mechanics and the theory of relativity. Eventually, if the white dwarf is left alone, it will radiate for billions of years before changing into a black dwarf. A black dwarf is a theoretical culmination of stellar evolution for which there is no empirical evidence, since the timescale necessary for its formation is significantly longer than the age of the universe. However, things may be very different if the white dwarf is a member of a binary star system. The white dwarf, for instance, is capable of absorbing mass from its companion star. Conditions for carbon fusion are improved as a result of the white dwarf's mass gradually growing as the compact star continues to accrete materials. Nuclear fusion begins when the mass passes the Chandrasekhar limit. Within a few seconds, a sizable portion of the white dwarf's mass experiences a runaway reaction, generating sufficient energy to release the star in a supernova explosion. That is how a Type 1A supernova works. Astronomers thought that NGC 1309 experienced an identical incident. In the years leading up to the supernova, Hubble repeatedly captured images of this spiral. Astronomers were then able to identify the progenitor star system, discovering that it had a white dwarf stealing material from an old helium-rich star that may have been a red giant. With these findings, researchers photographed a Type 1a supernova's progenitor for the first time ever. However, there appeared to be a problem with the Hubble readings. In addition to demonstrating the progenitor that had survived the explosion, the photos also revealed that the white dwarf was now considerably more bright than before. The occurrence is known as a supernova type 1ax. But how could this be? How did it manage to survive a supernova? To explain the observations, the experts looking into this incident have a partial idea. They contend that the white dwarf could not have been totally destroyed by the thermonuclear explosion. The majority of the material, however, returned to the star and inflated it, turning it into a bound remnant, which astronomers refers to as such. The star should eventually revert to its initial inactive state, according to astronomers. The star's increased brightness was also explained by the astronomers. The cause could be illumination from a number of sources, including the bound remnant's own glow, the shock-heated companion star that took the brunt of the explosion's energy, and the radioactive decay of debris that fled into space during the explosion. Astronomers have yet seen another odd tendency in the light curve of this supernova. A Type 1a supernova often uses cobalt radioactive decay to produce its light. Their respective half-lives are 77 and 221 days. This would indicate that the supernova's light considerably dims after a few years because the majority of the cobalt decays. However, the light is dissipating much more gradually in the situation of SN 2012Z. Furthermore, astronomers think that cobalt may not have been the chemical substance responsible for it if radioactive decay is the main source of light. This heightened light must be caused instead by a different isotope with a lengthier half-life. A 2.7-year half-life of iron-55 is what the team believes it to be. This discovery has brought up some important issues, just like every other worthwhile scientific finding. What causes a supernova to succeed as a Type 1a and fail as a Type 1ax, as well as what percentage of these explosions result in Type 1ax supernovas, are of utmost importance. The solutions to these queries will provide fresh perspectives on stellar astrophysics. And that is it for this video. Thank you so much for tuning in with us for yet another cosmic mystery unraveled. Comment down below which one you want to discover next, and we shall see you then.